is Lab 1, charge tapes. For the introduction, the purpose of this experiment was to determine the amount of excess charge on a piece of clear charge tape by charging two pieces and observing their interactions. Additionally, we developed computational models to compare the results. In terms of results, we found that for model 1, which assumed a point charge, the charge was measured at 1.35 times 10 to the negative 9 coulombs. For model 2, which assumed a line charge, the charge was smaller, measured at 7.89 times 10 to the negative 10 coulombs. The system in this experiment consisted of two charge tapes, while the surroundings included the supports, the base, and the environment. Fundamental principles, physics principles. According to Coulomb's law, the force between two charges is proportional to the product of the charges and inversely proportional to the square of the distance between them. Newton's second law tells us that when there is no acceleration, the net force must be zero. The electric field for a point charge is described as E equals kq over r squared. Finally, the gravitational force acting on the tapes can be described as F equals mg. Assumptions. Some key assumptions were made for our models. First, we assumed that the point charge is located at the center of the tape. With this in mind, the U-shaped tapes were modeled as a single point charge in the code. We also assumed that both tapes carried the same amount of charge and air resistance was ignored in both models. The lab. The procedure involved several steps. First, we placed a piece of tape on a smooth surface to serve as the neutral base. Then, two pieces of tape of the same size with U-shaped handles were positioned on top of the base tape. We charged the U-shaped tapes by quickly pulling them off the base tape. Next, we observed how the U-shaped tapes interacted with each other and other charged objects. Finally, we stacked one piece of tape above the other until the top tape began to flow, and we measured the distance between the tapes. Observations and initial conditions. Our initial conditions were as follows. The length of the tape was 0.2 meters with a mass of 0.0002 kilograms. The distance at which the tapes began to float was measured to be 0.003 meters. The gravitational force acting on the tapes was approximately 1.97 times 10 to the negative 3 newtons. The magnitude of the electric force was 1.98 times 10 to the negative 3 newtons. And the measured electric charge was 1.38 times 10 to the negative 9 coulombs. Computational model. We also created a computational model to compare the charge distribution. The charge, when modeled as a point charge, was 1.38 times 10 to the negative 9 coulombs. However, when modeled as a line charge, the charge was smaller, at 8.69 times 10 to the negative 10 coulombs. The computational model helped visualize how charge is distributed along the tapes and the interactions between the two tapes. Similarities and differences. When comparing the experimental data to the models, both the point charge and line charge models based on fundamental electrostatics. However, differences arise due to variations in assumptions. The line charge model, which integrates charge over the tape length, was more accurate for the charge tapes, which behave more like distributed charges. Coulomb's law and the inverse square dependence of electric fields still held true in both models, though the line charge model more closely matched the real behavior of the system, as it accounts for the tape's geometry. Possible errors. There were a few errors in the experiment. First, the line and point charges were calculated using different models. We also encountered inaccuracies in the tape measurements. Additionally, some incorrect assumptions were made during the lab. The line charge was smaller than the point charge estimate, which was expected given the tape's linear shape. Discussion. If the signs of the charges were reversed, meaning if electrons were positive and protons negative, there would be no difference in how tapes and charged objects behave. The two tapes would still have the same charge and repel each other, floating as they did in the experiment. The two computational values for the charge differ because they calculate the electric field in different ways. The point charge model used a single value, while the line charge model integrates over the entire tape. Since the tape is a linear object, the line charge model is more likely to represent the real value. In conclusion, the experiment demonstrated the behavior of charge tapes and highlighted the importance of choosing the right model to describe charge distribution. While there were some measurement errors and assumptions, the line charge model provided a more accurate representation of the system.